Welcome to Physical Science, Chapter 4. This is the chapter on heat and temperature. In this section, we will talk about the kinetic and molecular theory. As we learn about matter, in order to understand heat and temperature and the effects of heat and temperature on matter, we learn that all matter is made up of atoms and molecules. Atoms are made up of smaller particles, and these are called the subatomic particles. These are arranged in a specific way, and this helps us to identify the matter. In the case of matter made up of one kind of atom, the matter is described to be an element. Examples of element include hydrogen, oxygen, and gold. If matter is made up of more than one kind of atom, then the matter is described as a molecule. Examples of that include water, sugar, and alcohol. In this picture, the little blue balls represent atoms. H in the middle is the chemical symbol for the element hydrogen. So these two atoms together are two hydrogen atoms. If we add one oxygen atom to that, we end up with a molecule called H2O, also known as the molecule water. Now, as molecules get close, they interact. Their interaction depends on what type of particle is next to them. For example, atoms or molecules of the same kind experience an attractive force called the cohesive force or force of cohesion, while atoms or molecules of different kinds experience adhesive forces. In this section, we will talk about the different states of matter because the kinetic molecular theory affects or helps us to understand and explain the different states of matter. You see, matter makes up the universe and is made up of tiny particles, atoms, and molecules. And all matter, whether it's atoms or molecules, and depending on the type of compound we have, will exist in solid, liquid, gas, or plasma phase. The fifth state of matter is the Bose-Einstein condensate, and it's not really considered one of the four natural states because the Bose-Einstein condensate is man-made. Another name for the states of matter is the phase, or the phases of matter. The first phase we will talk about is the solid phase. A solid matter is made up of particles that are held tightly together. It has a definite shape and unchanging volume, and it does not follow the shape of the container. So we can have, for example, a cubic block of ice, and we can put that in a circular glass. It's not going to change the shape of our solid cube, of course, until it melts, it becomes a liquid. Now, the liquid phase or the liquid state, we have loosely held particles that flow around each other. Does not have a definite shape and will adjust to fit the shape of the container. So then the ice that's melted and is now water will become circular if the glass is cylindrical and has that circular shape. And all because the particles are loosely held together and can flow around each other. However, things change when we go on to the gas state. The particles in a gas are distant and have low attraction to each other. Gas has no definite shape or volume. It will spread out to fill its container as if uncovered or unsealed. It will continuously spread out. So if we have a container where the liquid has now evaporated and there's a gas, and we open up that container, all the gas molecules are going to go out and spread out in as much volume as will give us. So those molecules or atoms are going to go as far away from each other. That makes up the gas state. The plasma state or phase is similar to the gas, but with highly charged particles. It is an ionized gas when we have charged particles because they become ions, and it has the ability to conduct electricity since you have positive and negative charges. The negative charges are what will be responsible for the flow of the electric current. The sun right now is in the plasma state. You can also find plasmas in some neon signs and fluorescent lights. So let's check at how we can fit in temperature to these. Before we go there, we can also look back at these different states of matter and think about the energy or the interaction between the different states. If we look at the solid, the particles in the solid, there's not a whole lot of room to move. So as you can imagine, the kinetic energy of the molecules here, because they're not really moving, is much lower than the kinetic energy of the molecules that's in the liquid state, here where they can move around each other and flow. So now there's this movement and the kinetic energy has increased. So from the solid to the liquid, we have an increase in the kinetic energy. Similarly, when we get to the gas phase and they're moving away as far away from each other, they're very volatile, very high in energy, that they have enough to completely separate themselves and distance themselves from the other molecules. And so as we go from the liquid to the gas, again, we have an increase in the kinetic energy as the molecules are moving at a faster rate to get away, or because of the nature of gases. And so when we go from a solid to a liquid to a gas state, we actually increase in the kinetic energy. All right, so we're going to define our temperature. And there are 3 temperature scales that are used. We have the Fahrenheit scale, the Celsius scale, and the Kelvin scale. And these are reference scales that are used for measuring temperature. So if we look at the first scale, which is the Fahrenheit scale, we see there's a point, what we call the freezing point of water, and that's given as 32 degrees Fahrenheit. We see that there is another point where we have the boiling point of water, and that's 212 degrees Fahrenheit. And then we have our little equal divisions here between 212 and 232 degrees. Then when we look at the Celsius scale is designed to set the referent as water itself. Pure water is said to freeze at that certain temperature, which we know is 32 degrees Fahrenheit, but that's taken to be 0, the base for temperature, the 0 mark for temperature in degrees Celsius. So the freezing point of water is set at 0, and then the boiling point of water is just set at 100 degrees Celsius. And then we make 100 equal divisions between 0 and 100, and we get the Celsius scale. Now, if we look at the Fahrenheit scale and the Celsius scale, you see that the Fahrenheit is written as degrees Fahrenheit. Then you have a little circle here for degrees Celsius. But when we jump to the Kelvin scale, there is no degree Kelvin. That's because we just say the number 373, for example, up here, that's 373 Kelvin, whereas 100 degrees Celsius. So there's no degrees in Kelvin. Now, the Kelvin scale is sometimes called the absolute scale, because this gives the entire range of possible temperatures. The Kelvin scale go all the way or starts at what we call 0 Kelvin, which is negative 273 degrees Celsius or negative 459 degrees Fahrenheit. And that point is called absolute 0. And so from there, everything that's above absolute 0 will have some temperature in Kelvin or some positive value for its temperature in Kelvin. Absolute zero is theoretically thought to be the lowest possible temperature that can be attained. At this point, there's absolutely no motion at all, no vibration at all between any molecules in matter. In some books, you might see it described as matter being so close together, so highly compacted that it acts as one big superatom. So again, pay attention to our degree Fahrenheit, degree Celsius, and Kelvin, because they are very different. Now, when we want to convert from one temperature to another, it's really easy. You can take your smartphone, you can type your temperature that you have and the temperature that you want to get the value in. What happens when you type it to your smartphone is this, that the calculation is being done. So TF here stands for the temperature in Fahrenheit, and TC stands for the temperature in degrees Celsius. So here we have 9/5 of TC plus 32 degrees. So if we have the temperature in degrees Celsius, we multiply that by 9/5, and we take that number and then add 32 to it, we will get the temperature in degrees Fahrenheit. Also, if we have the temperature in degrees Fahrenheit, we take 32 away from that number and then multiply that by 5/9, we will get the temperature in degrees Celsius. So that's the calculations that we will do if we need to manually calculate those temperatures. Like I said, now we have free access to our smartphones where we can punch that into our search window and it will spit out whatever the temperature is in the units that we're interested in. If we want to get the temperature in Kelvin, all we have to do is add 273 Kelvin to the temperature in Celsius, and that's going to be our temperature in Kelvin. So 0 Kelvin is absolute zero. 0 degrees Celsius is given as 273 Kelvin. And then we just increase from there.